Okay, so now that we've recorded, as always, you can type your name into the chat so we have a record of your attendance. If you typed your name in before now, it will not be recorded. So you need to type it in again since I've started recording because I only get the list of everybody who types it in after um, after the um, after the meeting starts. Okay, so welcome back, everyone. Um, the I guess before we get to the math, I just wanted to know for the certification, do we have any update on when that's supposed to happen now? Do we know what's going on with the certification for the previous year?
Good afternoon to
Hmm.
everyone.
Right.
The certification program we it should have been held, but the Minister Cisco said we should hold on to it yet because we he was engaged with other activities, and then the team too were involved into this EdTech training for Liberian teachers. So I'm waiting on Masage to give go ahead because she some issue before we come out
Oh,
with a specific date. That was the problem that we had.
Okay.
Yes.
Okay. So we'll get more details, I guess, when we get them. To everybody who pointed out any mistake in their certificates. I sent out a couple of weeks ago on the chat everybody's name, and there were some people who had mistakes. Their name was written wrong or they were left off. I think most of the people for whom there's a problem already notified me. So I have the new certificates, but I have to talk to Mr. Randolph to figure out when they can be transported. They may not be able to be transported in time for the ceremony now, but we'll make sure that they get delivered to everybody who needs one. So I think Miata had her name wrong. I think Emmanuel had his name wrong. Rush had his name wrong. And I think Joyce was left off one of the lists. So it's all going to be fixed and we'll have it done. But if the certification ceremony ends up being next week or in 2 weeks, we may not have somebody to carry them to Liberia that fast. So hopefully we'll get them to you soon. But I have the new certificates, and we just need to find someone to carry them. And so,
Yes, that's Andrew.
yes.
Currently, Sange is in Virginia, Arlington, attending a program.
Oh, she's there
She's
right
there.
now.
Yes.
Okay.
So we have two persons that is there. One Julia sending me to as well.
Okay.
And Julia will be coming in 2 weeks. I think Sange within 3 weeks.
Okay. So
So
if any of
yeah.
them come to either New York or Philadelphia, then I'll bet I can either get it to them directly or Mr. Randolph can get it to them. So I'm going to give them to Mr. Randolph hopefully this weekend or early next week, Monday maybe. And so if some Virginia, probably we won't get all the way down there, but if anybody's coming further north to Philadelphia or New York, we can probably give it to them.
Yeah, sure. I will communicate with Sanke. She will talk to you about it and
Okay.
to see how best you can get it.
Okay, sounds good. Yeah, so I have them, and I can, and probably it's easier if I just give them to Mr. Randolph, and he can get them next week. Okay, thank you. Thank you for
Thank you.
reminding me of that. I knew Sanjay was coming, but I forgot when. Okay, so she's here now. Okay, good. Um, okay, so we will get that all worked out. Okay, great. Okay, so welcome back. So if you remember what we were doing last time, we were discussing logarithms and applications of logarithms. And I think one of these example problems with logarithms went by a little quickly, so I'm going to redo it again today. And then we'll move on to the next topic, which is going to be geometry for this workshop. So let's just first recall that we gave these are not the only applications of logarithms, but these are some good applications of logarithms in science. So we saw that we used logarithms to make these logarithmic scales. It was a useful way to present data that covers a large range. So one of our applications was pH, which measures the concentration of hydrogen ions in solution. And the range of possibilities is really huge. From a strong acid to a strong base, you have a very wide range of what the hydrogen concentration can be. Same thing for volume measured in decibels, which measures the sound pressure. That's what volume actually is. It's the pressure of the sound waves. And these also cover a huge range in everyday situations. So it turns out that logarithms were useful for measuring that. Then we have the Richter scale for earthquakes. Also, the difference between a strong earthquake and a weak earthquake is huge. So to make it put things on a more human scale, it helps to use logarithms. And then lastly, we have why can I? Oh, there we are. And so lastly, we have musical notes. I won't really talk about this as much, but the names for notes, what they really do is they measure the frequency of the corresponding vibrations, and that frequency is what our ear detects as pitch, as the pitch of that note. Okay, so let me be a little bit more specific about this. This is just the review from last time. What do all of these terms actually mean? So the in chemistry, the pH of a solution is defined to be negative log of A to base 10, where A is the concentration of hydrogen ions in the solution, and that concentration is measured in moles per liter. That's the chemistry unit that we use to measure that. In acoustics, the loudness of a sound in decibels is defined to be 10 times the log of B to base 10, where B is the intensity of the sound measured in appropriate pressure units. I'm not going to tell you the actual units. It's not just pascals or some standard pressure unit. It's scaled to make the decibel sound something that, uses numbers that make sense. But somehow, for the questions that we're going to deal with over here, we're not going to need to know what exactly the units are for this intensity of the sound. The pitch of a musical note is the frequency of its wave vibrations, and that's measured in hertz. Hertz just means waves per second. Okay. And we know that the ratio of frequencies between any two successive notes on the piano is 2 to the 1/12th. So again, I'm just recalling this from last time, but we're not really going to talk about it today. So what I want to just recall a little bit more today is this decibels. We're going to redo this example from last time a little bit slower so that we don't have to rush. So we have this example of a word problems from last time, which is so suppose a car driving by makes a sound measured at 70 decibels. Roughly how many cars would need to drive by at the same time to yield a sound level of 78 decibels? And we're going to assume that if n cars drive by at the same time, then the intensity of the sound is multiplied by n. So let me rewrite the formula. So we have the loudness in decibels is equal to 10 times the log base 10 of B, where this B is the sound intensity. Okay. Okay, so a car driving by makes a sound measured at 70 decibels. Roughly, how many cars would need to drive by at the same time to yield a sound level of 78 decibels, right? So if you recall how we do this, usually whenever you have some kind of word problem, it's a good idea to write down explicitly what your variables mean, right? So for instance, I could say, let B equal the sound intensity of one car, right? And so we know that one car is 70 decibels, right? So what that should mean is that we get that 70 equals 10, sorry, equals 10 times log of B to base 10. Okay. And this problem is asking us to solve for n. We want to know if n cars drive by, how many cars does it take to yield a sound level of 78 decibels? So we need to somehow solve for n, which means we need to write down an equation for n, right? An equation that's going to give us n. So let me just say strategy, write and solve an equation involving n, right? So we're going to write and solve an equation involving n. And well, what do we know? Well, we know that n cars gives a sound level of 78 decibels. Okay, 1 second. 1 second. Uh, we were there. I saw you. Okay. Okay. So, great. So, what do we have to do? Well, the idea is we know that if n cars drive by, well, if B is the sound intensity of one car, well, we know that NB is the sound intensity of n cars. Right? So if B is the sound intensity of one car, NB is the sound intensity of n cars, and we want to solve for n, that's going to give us a sound level of 78 decibels. So the equation that we get is going to be 78 equals 10 times log of NB to base 10. Okay. Oh, good. Okay. Everybody's coming in now. Okay. So the 78 gives us 10 log base 10 of NB. Okay. So now we have really two equations that we're working with, right? We know that 70 equals 10 log 10 of B, and 78 equals 10, equals 10 log 10 of NB. Right? So we need to now just combine these two equations to get something we want. And so the rest of this is just going to be algebra, right? This is, maybe I'll just write it. This is equation for one car, and this is the equation for n cars, right? So the equation for one car, and this is the equation for n cars. Okay. So now we just have to use this to solve for n. And in this case, I'm going to go over it a little quickly because we did this last time. We have to use the rules of logarithms. We know that the log of nb is the log of n plus the log of b. So I'm going to write these out on a new page. So what do we have here? Let's try to write it like this. So I'm just going to write these down again. So um, 70 equals 10 log 10 log 10 log 10 of B, and 78 equals 10 log 10 of NB. Well, this is equal to 10 log 10 of NB is log 10 of N plus log 10 log base 10 of B. And this is equal to 10 log base 10 of N plus 10 log base 10 of B. And what do we see here? Well, we have this equation, 70 equals 10 log base 10 of B. So this 10 log base 10 of B, we can substitute in 70 to make it work. So we can say again, this is equal to 10 log base 10 of N plus 70. This is the substitution. Okay. 70. So, and now we have an equation that's easy, right? So we use this first equation and the second equation with rules of logs to get that 78 equals 10 log base 10 of n plus 70. So now we can just solve this equation. We can subtract 70. What did I do here? No. We can just subtract 70 on both sides. So minus 70, we end up getting that 8 equals 10 log base 10 of n, and that tells us that zero point 0.8 equals log base 10 of n. And what that tells you by definition, if zero point 0.8 is log of 10, log of n to base 10, that's the same thing as saying that n equals 10 raised to the zero point 0.8. And you can write what that is. So what is 10 raised to the 0.8? 10 raised to the 0.8. You have to use a calculator for this. This is, roughly 6.3. Okay. So this is roughly 6.3. Okay. Okay, so what this tells us, remember, what was this n? You can't forget what the letters mean. The letters refer to the original things in your word problems. So n was 6.3. We were asking how many cars does it take to get the decibel rate up to about 78? And the answer is about 6.3 cars. So answer, you can be a little casual with the answer. So the answer is going to be 6 or 7 cars. Or you could say 6.3 cars. I mean, that's fine. It said about how many cars. So if you raise the intensity by a factor of, oh, sorry, let me do this. So if you raise the intensity by a factor of 6 or 7, then that's going to raise the decibels from 70 to 78. Okay. Sorry that people seem to be having some network issues today, so I apologize for that. I know that the fluctuations have gone in and out, so hopefully it will calm down. Okay, but so I just wanted to redo this problem from last time. Okay, any questions about how we worked this example? Okay. Okay, how does something become negative? Um, I don't see anything. Oh, no, this here, I'm just subtracting 70 from both sides of this equation. Right, so I'm just saying we have 78 equals 10 log n to base 10 plus 70, and so now I'm just subtracting 70 from both sides to get that 8 equals 10 log base 10 of n. Okay, nothing's becoming negative. I'm just subtracting 70 from both sides. Maybe it's easier if I put it in a different color. Let me write this, minus 70 and minus 70. Okay, and then I'll put it in a different color. Okay, other questions? Okay, so I didn't receive any solutions to this, but I don't know if anybody had one. So did anybody do the homework exercise, which was to come up with a word problem involving an application of logarithms and then solve the problem? Maybe we can do, one of your problems, if anybody has come up with one of these problems. If not, you can think about it for another week, and we can do one next week.
Yeah, God.
Yes.
I beg, can we regress a little
Mm-hmm.
on the problem?
Mm-hmm.
Please put it on the screen.
Yeah. So this one.
Yeah,
Okay.
yeah, okay, okay. Thank you. So
Okay.
I don't know, will you please go over this part where you have representing the loudness, which is dB, in terms of the sound intensity. Can you please go over a little, please?
Sure. I mean, so you should think of this. Let me mute you just because there's some background noise. Sure. So this really is a definition. This is the definition of the decibels scale, right? And the point is that the decibels scale is a logarithmic scale. So for most measurements you take, they're direct measurements. If I say that I'm 6 feet tall, then somebody who's half as tall as me is 3 feet tall, right? If I double my height, I double the number of feet, right? It's very straightforward. If I say that something weighs 100 pounds and I take something twice as heavy, that weighs 200 pounds, right? It's just a simple proportion for how most things are measured. But it turns out that, that's not a good way of measuring sound because I showed this chart in the slides last time. If you talk about a whisper or a jet plane, then the intensity of the jet plane is about, 100 billion times the intensity of the whisper, right? So you just start to get big units that don't make any sense if you just try to directly say, this is the intensity of the sound. So the point of the decibels scale is to try to be able to say things about the intensity of a sound in kind of standard numbers that humans can understand. Okay, like okay, a car that's 70 decibels, a helicopter that's maybe 120 decibels. I don't have the chart right now, but if you look at the at what I sent out last class in the notes there, there's a chart which shows how many decibels various common various common common sounds are, right? So the question is, how do you turn something like loudness, which varies so much when you think about the actual physical units? The actual physical unit is the pressure of a sound wave. That's what loudness is. And these physical units vary so widely that it's very hard, something that's a million sound units or a billion sound units, it's hard for people to really understand the difference between them. Whereas something that's 70 decibels or 100 decibels, that's a little bit easier. So it turns out the way to kind of compress this scale in a way that makes sense is to use logarithms. And so what this thing here is, this loudness equals 10 log of b to base 10, this is just a definition. Okay? There's a unit where you can measure sound intensity. That's a direct unit. And if you take the log of that unit to base 10 and then multiply by 10, you get this other unit called decibels. And decibels is just the universal world unit for measuring how loud a sound is. Okay, everybody uses decibels. All amplifiers for, musical instruments are, they're standardized in decibels, like how many decibels does this add to the sound and so on. So this formula here, there's not that much to explain. It's just, I could say the loudness equals 10 log 10 of B, where the loudness here is L measured in decibels, and the B here is the intensity of sound measured in some sort of pressure unit, which is not really so important what the unit is, because nobody uses the pressure units. Everybody uses decibels. Okay? So this is just the definition of how you know how many decibels a sound is. You measure its intensity, and then you do this math to it. So for the problem, I'm just telling you that a car driving by makes a sound of 70 decibels. So let's say you're designing a highway, right? And you want to know how loud is the highway going to be for the people nearby, right? That's going to depend on how much traffic there is, right? How many cars are driving by at any given time, right? And so we want to know what happens. But the point is that decibels don't work like standard sounds. So if one car drives by and makes a sound of 70 decibels, then two cars does not make 140 decibels. That's not the way decibels work. That's not the way the units work, right? You would say normally, okay, if one car makes 70, then two cars make 140. But that clearly just doesn't work. 140 decibels is completely deafening. You'd blow out your hearing. So instead, it works in this kind of strange way that we're trying to understand for this problem. So I can go back over the problem quickly, but the point is what we showed at the end of the problem is that if you have 6 or 7 cars driving by at the same time, the sound actually goes from 70 decibels to 78 decibels. And that's kind of the way of saying that, well, 6 cars is not that much louder than one car. you certainly don't perceive six cars as being six times louder than one car, right? It seems like six cars is a little louder than one car, but it's not really six times as loud, right? And so what happens actually that we see is that six cars, you go from 70 decibels to about 78 decibels, right? It's not that much louder. Okay. So to go back with this equation, why do we have this 10 log 10 of B? This is just how the decibel scale is defined. Okay. And so we know that if B is the sound intensity of one car, we have that 70 equals 10 log 10 of B. That's saying if B is the sound intensity, then the number of decibels, the loudness, is 70. And now we want to know for N cars, NB is the sound intensity. And 78, where we want to know how many cars does it take to get a sound level of 78 decibels. So if you have NB cars, that's going to give you 78 decibels. And now the question is to solve for N. We basically have two equations that involve two variables, N and B, but the only variable we care about solving for is N. And so with what we do in the equation on the second page is really about how we use these two equations to solve for N. So Emmanuel, I know that was a long answer. Does that give you what you want, or is there a part of it that you'd like me to focus on?
Thank you, thank you.
Okay.
It's blessed.
Okay, you're welcome. Any other questions on this one? Or we can also go back if anybody had a word problem. Mhm. Okay. I think okay. So maybe let's, in addition to the homework for this week, if anybody else would like to try to write a word problem to present next week for doing an application of logarithms, we'll do that. Okay, so maybe we'll skip this now if people aren't prepared. So we'll do this next week. Okay, so I mean, it can be any application you want, but if you want to model something in terms of decibels or something in terms of pH or something in terms of the Richter scale or musical notes, are things that you have some notes on that you can look at to see if there's an application that you'd like to present in a problem. Okay. So if that's it, then to let's actually move on to the next unit if nobody has any more questions. Okay. Okay. Well, okay, so you can present it if you want next week. Okay. All right. So today's topic, okay, yeah, so Enoch, yeah, you can present it next week if you want. Yeah, you can send it to me also. Um, Okay, so today's topic, I'm looking at certain topics in the curriculum in the 10 through 12 Math Liberia curriculum that I think will benefit from this treatment of trying to think about things at a somewhat deeper level, as a teacher that will help us when we're teaching students. So geometry is, of course, it's a big part of the topic. It's a big part of the curriculum, and it's something that I think a lot of students struggle with. So we're going to spend a few weeks discussing geometry. But for today, I want to do just one little topic inside geometry. And so this is a topic in geometry called mensuration, or mensuration. Um, and so what is it? I mean, it's very basic. It just means measuring things, right? It's the act of using geometry to compute lengths and areas and volumes of shapes. And there are lots of formulas that are available for these computations. Some of them are very, very simple. Some of them are more complicated. Some of them are easy to rederive them if you forget them, and some are not so easy to rederive if you forget them. So I want to recall some of these formulas today. I mean, and that would be not so interesting. I mean, okay, you know how to calculate the area of a triangle or the circumference of a circle or something like that. Oh, I see. I see. We have a an exponential growth word problem. Okay, great. Let's Linford, let's table this one. Let's do it next week. Okay. This is kind of an exponential growth one, but this would be a good a good problem to use. Okay. So let's if you can save this problem, let's do it next week. Okay. Um so um so now of course you can just memorize all the formulas, right? And in the end, that's what students will often have to do. They're going to have to memorize formulas if they want to be able to, measure things in geometry, compute volumes and areas and surface areas and lengths. They're going to need to know the formulas. But what I do want to talk about today is some ideas that will make it a little bit easier to remember which formulas make sense for which quantities. It's a good way to check to see if your formula, if you don't remember whether your formula is the right one or not. This is a good way to check in your mind to see, does it make sense or does it not? So we'll talk about this today, right? So let's start the most basic thing. So the simplest quantities to measure are one-dimensional quantities. So like perimeter and arc length. So let's start at the very, very basic formulas. So what is the perimeter of a regular n-gon with side length s? So remember, a regular n-gon just means, all sides equal and all angles equal. And when I say an n-gon, that just means n sides. So if I have a regular n-gon, a shape with n sides, and each side has length s, what's its perimeter? This is meant to be an easy question.
BS.
Yeah, s. So s is the length of each side. Yep. So s times.
Hello.
Yes, hello,
Um,
Rush.
um,
For the parameter for the polygon,
Hmm.
P is equal to ns,
Yeah,
which is the
exactly.
number multiplied by the size.
Exactly. Right. Just going to be. Why can't I do this? Right. It's just s times n. Right. I mean, this is the side length, and this is the number of sides. Right. I mean, so this is the perimeter, right? You've got n sides, and the side length is s, and so if you want the total perimeter, it's just going to be the number of sides times the side length. That gives you the entire perimeter of the shape, right? So this is a pretty simple formula, right? Example, of course, would be, if n equals 4, you have a square. And if you have a square where every side is length s, then the perimeter equals 4s. Right. Okay, so nothing tricky here. So second thing, what is the circumference of a circle with radius r? This is one of these formulas that you either know it or you don't. So you have your circumference.
Yeah,
Sorry, yes,
yeah, the circumference of the circle is equal to 2 pi r.
right.
Yeah, it's equal to 2 pi r. The reason I'm not talking is that I was in the noise. I was just in class. I just coming here.
Okay.
That's how. Yeah.
Okay, that's fine. All right. Welcome, welcome. Okay, so the circumference is 2 pi r. This is maybe not as easy to derive. I mean, one way to think about this, I mentioned this in the calculus class last year, you should really think of this as the definition of pi, right? What is pi? It's the ratio of the circumference of the circle to 2 times the radius, right? Pi equals c over 2r or c over the diameter, right? So pi is the ratio of the circumference to the diameter of a circle, right? You should think of this as really saying that that ratio is constant, and we call that constant pi. Okay, so c equals 2 pi r. This is fine. This is the formula for circumference of a circle. And now we have number 3, which is not a formula that anybody's really memorized. But what is the perimeter of a right triangle with hypotenuse h and
Yeah,
angle theta? So I'm just going to draw it. So if this is h and this is theta, yeah,
yeah, yeah.
yeah,
That about?
yes,
Yeah, the thing is that once you are giving such information, the first thing I just want to explain a little bit about it is that the perimeter of a right angle with hypotenuse h is that the h is always the longer side of the hypotenuse, and once you have an angle based on whatever location you have, the hypotenuse remain the hypotenuse, and what the relationship between them will be. For example, if you are looking for such formula, it should involve both sine and that of cosine, which will
mhm,
be in a form, for example, yeah, you have the perimeter will be equal to, you can say the hypotenuse times the sine of that particular angle
mhm,
plus the same hypotenuse times cosine of that angle plus the hypotenuse. So if you
right,
let you cannot factor out the hypotenuse.
mhm,
Yeah, so it will lead to the perimeter is equal to h parenthesis. You can represent the hypotenuse with h, you can represent it with x, y, or whatever value you like. So you can
mhm,
say P is equal to h parenthesis open, sine
mhm.
of the angle theta, sine of the angle theta, you can say theta, beta, or whatever stuff,
Right, we'll call it theta.
plus,
Yeah.
okay, plus cos of theta plus 1. A
Okay.
parenthesis close.
Great. Perfect. Right? So this is not a formula that people have memorized, but it's something that you can figure out for yourself if you want. You have a right triangle with h as your hypotenuse and theta as one of your angles. You can figure out the other two sides using right triangle trigonometry. We'll talk a little bit more about trigonometry later. It's not the focus of today. So let me just remind you that this side will have length h times sine of theta, and this side will have length h times cosine of theta. That's because sine of theta is the ratio of the opposite side to the hypotenuse, and cosine of theta is the ratio of the adjacent side to the hypotenuse. We'll talk more about trigonometry later. And so the perimeter is just the sum of all three sides. So that's h plus h cosine theta plus h sine theta. And you can also pull out a factor of h, and you can get this 1 plus cosine theta plus sine theta. Okay. So, yeah. So we have these three formulas, and they all look different from each other, right? One is s times n, one is 2 pi r, and one is h times 1 plus cosine theta plus sine theta. Okay, they look like different kinds of formulas. But what I'm going to want to argue, not yet, is that these formulas are all, they share something in common. That they're all measuring one-dimensional quantities, and that's going to make them share something in common. Sorry, was a question?
Yeah, I wanted to say something. Yeah, in this case,
Hmm.
the perimeter of the right triangle. What can you say about its perimeter when the angle is 0? It is possible that angle be 0 or whatever stuff. Can you
Right.
say?
Well, so if the angle is 0, if you're looking at this degenerate case where the angle is 0, right? So if I had theta equals 0, then what does that look like? That basically looks like the right triangle just becomes a line,
Yeah,
basically.
because
This,
the only thing you can say, for example,
yeah,
when you are referring to this, it can be in a case where you are talking to a person on angle elevation and that of depression.
yeah.
So if you are, yeah, this case it will be where the person look directly above sea level with, for example, without any angle. So the angle there will be directly 0.
Hmm. And so yeah, so let's see. It's sometimes it's good to analyze these degenerate cases. So what does the formula give you if the angle is 0? Well, if you go over the trigonometry, cosine of 0 is 1 and sine of 0 is 0. So this in the parentheses becomes 1 plus 1 plus 0, which is 2. So the formula that you get is 2h. And what you have over here actually is that your this is the hypotenuse. You're thinking of the hypotenuse kind of in this degenerate case, kind of collapsing to the horizontal. And the perimeter, what's really going on is that this triangle, the hypotenuse and this bottom side are really the same side. So what happens is the height of the triangle shrinks to 0, and the hypotenuse and the bottom side are each h because they're both the same. And so the 2h kind of makes sense because you think of the perimeter as going from one point to another point along the hypotenuse and then going back along the bottom side. So you're really counting this h twice, right? So that's a way to interpret this formula as making sense even when theta is equal to 0. You could call this perimeter 2h, right? To get from you to this person at eye level and back, which is what a perimeter does. It makes a total cycle. So over here, you're really getting out to the point and back. That's a distance of 2h because it's h out and h back. And if you plug in theta equals 0 to this formula, you also get 2h. So that's a way of interpreting this when theta equals 0, but it's just an interpretation, right? Because perimeter, to define it, we need an actual shape, not something degenerate. So this is an interpretation of a way that you could make sense of this formula when theta equals 0. But the formula in and of itself, really, if it's for a triangle, it needs to be an actual triangle. But you can still interpret it when theta is equal to 0. Okay, and then you would get 2h equals 2h. Okay, other questions?
Hello, Boss.
Yes, James.
Yeah. I got a question for theta because if you look at the triangle there, theta is opposite the right angle. So why if theta is up? That means let's say it's in
Up
the
here.
upper direction.
Right. So it's
Yeah.
going to be the same thing, but this side will be h sine theta and this side will be h cosine theta. But the perimeter is not going to change. Right? Because if theta's up here, you're just going to switch what these two sides are. I mean, basically, imagine you could take this triangle and you flip it so that this theta is up here. You turn it over and rotate it so theta's up here. It's not going to change the perimeter, right? Because you're just moving it around and rotating and flipping. So that doesn't change the perimeter.
Okay, thank you, sir.
Yeah, you're welcome. Other questions?
Hello.
Hello, yes. Raj.
Yeah. Just like if the angle is being shift upward, right, which is vertical upward, when you think which is the opposite and adjacent which we shift little bit, right? Like example, right now what the angle is now if the angle is being placed upward now, which is vertical upward,
Meaning if
which
the
means
angle's over here?
yeah, sure. Which means the adjacent side will come to the opposite position, like it will be now we call.
Mhm.
Then what the opposite side will come to the adjacent side, right?
Right, exactly. Because imagine, so here's what you can do with this to shift it upward. Imagine, I can't animate this, unfortunately, but imagine I take this triangle and I rotate it so that this theta is on the top.
Okay.
And then I could flip the triangle over. And now what you have is that the right angle is in the same place, but now theta's on the top and this other angle is on the bottom. And the sides are rearranged, but it doesn't affect the perimeter. Because you still have the three sides are the same length, they're just switched with each other. Is that okay?
Hello.
Hello, yes?
Yeah, I understand. Thanks.
Okay, good. Anything else? Okay. Okay, so let's move on. So these are one-dimensional quantities, and I'm not claiming this is every one-dimensional mensuration formula, but it's some representative ones. Okay, so let's talk about two-dimensional quantities. So we can do two-dimensional quantities. So for instance, areas of some regions in the plane. So what are, basic examples of area formulas, right? Well, we could have, a rectangle, right? If I have a rectangle, this is maybe the most basic one. If I have a rectangle with a length W and a height H, then the rectangle, the area is equal to the length times the height, for instance. Um, or if I have a circle, if this is a circle with radius r, then we know that the area is equal to pi r squared. Not so easy to derive. We did it in calculus last year, but without calculus, this is actually not very easy to figure out. So, but you know it just because you've seen it. So this is the area is pi times r squared. We know that a triangle, for instance, is if I look at a triangle here, if this side over here we call the base, and this side up here is the height, then we know that the area of a triangle equals 1/2 base times height, and so on. I guess we could do another one. There's lots of different areas for triangles, so you could also write if I have a triangle, for instance, like this, and if I label the sides A and B over here, and I label this angle theta, then there's another formula that relies on trigonometry, which I'm not going to prove for you, but you could say that this is 1/2 times A times B times sine of theta. For instance, this is another formula for the area of a triangle. They're both correct in this case. And there's more. You could do a parallelogram. I think if you were in the class a few years ago, we did the area of a general regular n-gon. This was some formula that involved trigonometric functions of 180 degrees divided by the number of sides. It was a pretty complicated formula. Not that hard to derive, but not so easy to memorize. So the point is, there's lots of examples of different area formulas that you can have. Okay, and these are maybe three of the most basic, but certainly you can do parallelograms, trapezoids, anything else that you want. And these all have. Does anybody else have a favorite area formula of a two-dimensional shape that's not one that I've written here so far? And maybe we have room for one more.
Hello?
Hello, yes.
Are you asking? I
Yeah,
don't
did
get
you have
you.
another area formula for some other shape that you want to add to our list?
Or error?
Yeah, an area formula for a shape.
Yes.
Yes.
All right.
Sorry, Rush.
No, I mean, the language is different, right?
Sorry, I'm not getting you well. Sorry. Yeah, I'm not getting you so well. It's not clear.
Hello?
Hello, yes.
Yeah, for square.
For square. Okay, great. Square. Great.
A is equal to x and x or x square.
Okay, great. Yeah, so square with side length s, we have that area equals s squared. Perfect. Okay, great. Okay, so these are all different formulas. They're all different. I claim they also have something in common, which we'll see in a little bit. Okay.
Yeah, sorry.
Yeah. So I'll say, what are other two-dimensional formulas? So we have the area of a shape in the plane, but you can have another kind of two-dimensional quantity, which would be a surface area of a three-dimensional shape. So you can have the surface area of a cube or a rectangular prism or a sphere or a cone or a pyramid. And often you can derive these formulas from plane formulas, right? So what's an example? Maybe the first example would be a cube, right? If I have a cube with side length s everywhere, then a cube has 6 sides, right? So the surface area Well, the cube has six sides, and each side is a square with, I mean, six faces, right? And each side is a square with side length s. So the total surface area is going to be 6 times the
S
area of
square.
each side. Exactly, right? So 6 times s squared. That's going to be the surface area of a cube. Um, I have what's called a rectangular prism. So this is kind of
Rectangular.
like a cube, but we just don't assume that the sides are all the same length. So let me redraw that line. Let me just redraw this. Yeah. So if this is L and this is W and this is H, so this is the length, the width, and the height, right? So this height here is
Both appear
H, this
flat.
here is W, this is L. Then we need to figure out the surface area of this. So a rectangular prism is like a cube. It also has six faces, but now each of the different six faces has different areas, right? So this side has area WL, this has area HL, this has area WH. So what do we actually get when we calculate the surface area of this shape?
So the surface area will be
Yep.
Is equal to
Sorry, James was going to answer. Yep.
SA
S square
equal
Yeah. James?
2 parenthesis open
Hmm.
W plus H plus WH.
So right, so WH plus, right? So that's going to give us the WH is going to give us these two, this side and the side opposite it, which we can't really see. So this side and
Yeah.
this side. And what about for the top and the bottom?
Dr. Andrew.
Yes, Jasper.
Yeah, yeah. So what if we say surface area will be equal to 2 times WL plus HL plus HW?
Yeah, exactly. I'm rewriting this in a different order, but it's the same thing. Yeah,
Yeah,
exactly.
okay.
So it's 2 times WH plus WL plus HL. The idea is you've got
Yeah,
two sides that are WL, that's the top and the bottom. You've got two sides that are WH, that's the right side and the left side. And you've got two
okay.
sides that are HL, that's the front and the back, right? Because they're both rectangles. And so when you take all six sides together, this is what you get. You get 2 times WH plus WL plus HL. Okay, and then there's some more complicated ones, which I'll write down. So for a sphere, so if I have a sphere that looks like this, maybe this is my sphere, and it has radius r, then you can calculate the surface area of this. Not really any way to do this other than calculus. I don't remember whether we did it last year or not. Probably not. But the surface area of the sphere turns out to be 4 pi r squared when r is the radius. Um, and then you have other ones. Maybe I'll just do a cone. So a cone, and when I say a cone, I mean a right circular cone. So a cone I'm going to draw like this. So this is my cone. It's a circle on the base, and it comes to a point on the top. And so it turns out that if the cone has the side length, this is called L, and if over here the radius of the circle is R, it turns out that the surface area is equal to pi r squared plus plus pi r L. That turns out to be the surface area. Okay. So, and I'm not going to derive this for you. Again, a satisfying derivation of this really is going to use calculus. But let me just leave this as the surface area. So again, we have a bunch of surface area formulas, and I'm not going to do the pyramid just because we don't have space for it. Okay, we can do the pyramid a little later. But for now, we have these surface area formulas. Sometimes you can derive them from simple formulas about shapes. That's when the surfaces are straight. And then sometimes when the surfaces are curved, it's not so easy, right? I mean, understanding a sphere and a cone, you wouldn't be able to just like draw some lines and come up with this, right? I mean, it really requires some calculus. But regardless of whether you understand the calculus or not, you can understand the formula. Okay, the sphere, what's the surface area? Well, if you know the radius, it's 4 times pi times the square of the radius. And for a cone, it's what's the surface area? It's pi r squared. That gives you the surface area of the circle on the bottom, plus pi rl, which gives you the lateral surface area of the cone, this part on the top. Okay, so this is a two-dimensional quantity, surface area of a three-dimensional shape. Okay, questions? Okay, so we also have three-dimensional quantities, which are known as volumes. And we can do this for the same shapes that we mentioned on the previous slide. So let's just do the same four shapes, right? So a cube, right? We have S, S, and S. Every side is S. Then the volume is equal to, so what's the volume of a cube here is just going to be S cubed, right? That is why we call it cubed, right? Because it's the volume of a cube. The next one that we had is a rectangular prism. Okay, so I'll draw the same picture I did before. So if this is, I want to just label it the same way. Okay, so if this is H, this is L, this is W, this is H again. We have W over here, this is L. Then the volume of the rectangular prism, we just multiply all of the three different measurements together, right? So we have volume equals length times width times height. Great. We had a sphere. It's another one of these volumes that's hard to do without calculus, but you can do it. So the volume of a sphere, okay, with radius r, turns out that the volume is equal to 4/3 times pi times the cube of the radius. Okay, again, not something that would be easy to come up with. How would you know to do this? 4/3, that seems pretty hard. Okay, and then for a cone, okay, and then for a cone, you have for a cone, I'm gonna give the dimensions of the cone slightly differently. So I'm gonna let me draw this. Let me change my drawing of this. So if I have a cone like this, if this is my cone and this is the radius of the cone, now instead of giving the length of the side of the cone, I'm going to give the height of the cone. So straight up from the center to the point. And in this case, the volume of the cone is going to be equal to 1/3 times pi r squared times h. Okay. Okay, so these are some other formulas, some other volumes that you get, and again, they all look a little bit different, but they all have something in common. Okay, so these are all these same shapes as mentioned on the previous slide. The volume formulas are actually, I don't know, for me, they're actually a little easier to memorize than the surface area formulas, but in the end, they're formulas, and they're just formulas that you have to know, and they're just formulas that your students will have to know. But what I want to do is try to talk about what are better ways to remember these formulas, or at least to like check that these formulas make some sense. Okay, so before I move on to that, any questions about the formulas themselves? Okay. Okay. So let's move on. All right. So okay, so what do these formulas have in common? So let me recall these one-dimensional formulas, okay? So we saw that the perimeter of a regular n-gon with side length s was Sn. The circumference of a circle was 2 pi r. And the perimeter of a right triangle with hypotenuse h and angle theta was h times 1 plus sine theta plus 1 times cosine theta. We didn't do this one, but if you also have a circular arc with radius r and angle theta, so I'll call this a circular arc, a wedge of pizza. This is angle theta, and the circle has radius r, and let's say that our angle theta here is measured in radians. Then by definition, this arc length of this circular arc here has arc length is r times theta. Okay, this is the definition of radians. It's another way of saying that. You know, the radians tell you that if an angle is theta radians and your circle is radius r, then this arc length is exactly r times theta, which means in particular, if your angle is 1 radian, what does 1 radian mean? It's an angle that's just big enough to make this arc length equal to r. And turns out that a radian is about 57 degrees. Okay, it's 180 divided by pi degrees. But this is what you get. So this arc length is r times theta. So let's look what happens. So what happens to the circumference or the perimeter in any of these formulas when you multiply all length inputs by a scaling factor c? Okay? So if I say I'm going to make the figure, I'm going to scale it by a factor of c. So I'm going to make all the sides twice as big. Okay? So if I replace s with cs, let's actually maybe let me write the cases separately. So let's say first we have, for the n-gon, so this is number 1 for the n-gon. So I have the perimeter equals Sn. If s is replaced with cs, so that means I multiply the side length by c, then the new perimeter is equal to cs times n, which is c times Sn. So what does that mean? The perimeter gets multiplied by c. Right? If I multiply the side length by c, I multiply the perimeter by c. Right? So if s is replaced by cs, then the perimeter is instead of Sn, it's now CSN. It gets multiplied by c. Right? And similarly for these other formulas, right? So for the circle, right, I have that the circumference equals 2 pi r. Well, what is a length input here? Pi is not a length input. Pi is just a number, right? A radius is a length, right? So if I replace the radius with c times the radius, then my new circumference is equal to 2 pi times little c times the radius, which I could pull out the c, that's little c times 2 pi r. And again, what we see here is that the circumference gets multiplied by c. Circumference gets multiplied by little c, right? So if I have an n-gon and I multiply the side length by c, the perimeter gets multiplied by c. If I have a circle and the side length, or the radius in this case, gets multiplied by c, then the circumference also gets multiplied by c. What happens if I have this right triangle? Same thing, I'll write it on a new page. So I'll just remember for, right triangle, right, for the right triangle, we have that the perimeter was equal to h times 1 plus sine theta plus cosine theta. Well, what is a length input? This hypotenuse is a length. The angles are, theta is not a length. If I stretch the triangle by a factor of 2, the angles stay the same. The angles don't become twice as big, right? Only the length is stretched by a factor of 2. So if we replace h with 2h, then the new perimeter is now going to be 2h times 1 plus sine theta plus cosine theta. In particular, the perimeter. Oh, sorry, I don't want to call this h. I don't want to call this 2. Let me call it c. ch. Then the new perimeter is ch times this. So the perimeter also gets multiplied by c. And lastly, for the last example, which is a circular arc length, so a circular arc length, I'll call it AL. Our formula from the previous page was equal to r theta. Well, if r, the radius of my circle, gets multiplied by c, then the new arc length is CR times theta, which is C r theta. And again, what we have is that the arc length gets multiplied by C. Okay? So in all of these cases, even though these formulas all look different, Sn 2 pi r, h times 1 plus sine theta plus cosine theta, r theta, these are all different things. They all have this property that if you multiply your length inputs by c, then the output, the perimeter or the circumference or whatever length it is, whatever one-dimensional thing it is that you're trying to measure, also gets multiplied by the same constant c. So if I double all my lengths, input lengths, I double the perimeter, right? If I triple all of my input lengths, I triple the perimeter. Whatever I do to the input lengths, the same thing happens to the perimeter. It gets multiplied by the same thing. Even though all of these formulas look different, in every case, multiplying your inputs by C is going to multiply the output by C also. Okay? Okay. Any questions? Okay. All right, great. So let's move on. So what happens when we do these two-dimensional formulas? So let me just do, let's just rewrite these formulas that we have from before. So these two-dimensional formulas was a rectangle. So where are we? So a rectangle, we had that the area was equal to L times H. A circle, we had that the area was equal to pi times r squared. Triangle, we had that the area was equal to 1/2 base times height, or you could also write that the area was equal to 1/2 times 2 sides times the sine of the angle between them. And we also have square, that the area was equal to s squared. So we had all of these different area formulas. Well, what happens when we multiply all of these length inputs by a scaling factor c? We're going to have the same. So like you have your rectangle, your circle, your triangle, you stretch everything by a factor of c. Maybe you double the size. You make the radius twice as big. You make the sides twice as long. Well, we'll see our pattern, right? So rectangle, if c, so if all of our inputs get multiplied by c, so if L becomes CL and H becomes CH, then the area becomes what? It becomes CL times CH, right? If I multiply the length and the height by C, then these each get multiplied by C, and if I simplify this, this becomes C squared LH, right? So what happens is that the area gets multiplied by C squared. Okay, right? So if I multiply each of the sides, if I stretch them each by C, then the area is going to get multiplied by C squared. Same thing with the circle, right? So if the radius, which is my only length input, again, pi is not a length input. Pi is just a constant, right? Yes, I will. We're doing volume with 3. Yes. So if we're going to do that in a second. We already did a little. We'll do a little more. Right? So again, C squared for James. Exactly right. So if R gets replaced with CR, then the area becomes, instead of pi r squared, it becomes pi CR squared, which when we simplify this, this is pi c squared r squared, or in other words, c squared times pi r squared. And what this tells us again is that area gets multiplied, sorry, there's not enough space to read this, again by c squared. Okay, so the area again gets multiplied by c squared. And maybe I won't do it, I'll just leave it as an exercise for the other two. So exercise, show that for triangle and square formulas, scaling all sides by C scales the area by C squared. Okay. For the triangle and square formula, scaling all the sides by C scales the area by C squared. Okay. Okay. So in all of these two-dimensional formulas, this is why it's called two-dimensional, is if you multiply your length inputs by C, your area is actually getting multiplied by C squared. So for instance, you have a student who's like, oh, I never remember whether the formula for the area of a circle is pi r squared or is it 2 pi r, right? You get mixed up with the circumference versus the area. Well, one way to make sure that you're not mixed up is that you know if it's an area formula, if you multiply the input by C, then the area has to get multiplied by C squared. Okay? So you can try the two different formulas. You can try, if you try 2 pi r, if you try pi r squared, what happens when you replace that r with CR? Does the final answer get multiplied by C or does it get multiplied by C squared? And it turns out that, and so it turns out that only for pi r squared does it get multiplied by C squared. Okay? So you know if you're checking an area formula and you're not sure that if it's right, one thing to check is, does it have this property that if I multiply the inputs by C, does the output get multiplied by C squared? And for any area at all, that has to be the case. Okay? What about and so by the way, maybe I should say this also holds true for surface areas. So maybe I'll say, I'm not going to write it down in detail, but I'm going to say the same principle holds for surface area formulas. So that says that if the length inputs get multiplied by C, that causes the surface area to get multiplied by c squared. Okay, this is the same for surface areas, right? And just going back, for instance, what's one of these surface area formulas, right? Over here, if I multiply all of W, H, and L by C, then the whole surface area will get multiplied by C squared. Here, if I multiply R by C, then the entire surface area will get multiplied by C squared. Here, what are my length inputs? It's R and L are both lengths. If I multiply both R and L by C, you can verify that this surface area will get multiplied by C squared. Okay, so these are all exercises, but anytime you multiply your inputs by C, your output is getting multiplied by c squared. That holds for regular area, and it also holds for surface area. Okay, so let me go to Hassan's question now. What happens with volume? So we have our three-dimensional formulas for volume, right? So we had that a cube, the volume was equal to s cube, rectangular prism, rectangular prism, we had that the volume was equal to length times width times height. For a sphere, we had that the volume was equal to 4/3 pi r cubed. And for the cone, we had that the volume was equal to 1/3 pi r squared h. Right? These are the formulas that we had earlier in the, we wrote these formulas over here on slide number 10. Okay? So we have these all done. I'm just copying the formulas again. Okay, so if I copy these formulas, what happens to the volume when we multiply all the length inputs by a scaling factor c? Same as scaling the figure by c. I'm just going to do one example. Let me just do the cone. So for the cone, what do we have? So if r gets multiplied by c, so r becomes cr, and h, which is also a length, that becomes ch, then what happens to the volume? The volume becomes 1/3 pi, and then r squared h. R is now cr, so we have cr squared, and h is now ch, so we have ch. And if we simplify this, this becomes 1/3 pi c squared r squared ch, and I can pull out all of the c's, and this ends up becoming c cubed times 1/3 pi r squared h, right? And so what's actually happening here? This says that the volume gets multiplied by c cubed. Okay, volume gets multiplied by c cubed, and I'll leave it as an exercise. Exercise, check that in all cases here, that multiplying length inputs by c multiplies the volume by c cubed. Okay. Right? And so this is, this kind of makes sense, right? For one-dimensional things, multiplying the inputs by c multiplied perimeters by c. For two-dimensional things, multiplying inputs by c multiplies areas by c squared. For three-dimensional things, multiplying inputs by c multiplies volumes by c cubed. That exponent is the dimension, right? It's saying if you scale your lengths by something, then your volume will be scaled by that same factor raised to a certain exponent. And that exponent is exactly the dimension of the figure that you're looking at, right? So if you're looking at a volume, a three-dimensional figure, that exponent's going to be 3. If you're looking at an area for a two-dimensional figure or a surface area of a three-dimensional figure, as long as it's an area, that is going to be 2 in the exponent. And if it's a perimeter or a length, then it's always going to be 1 in the exponent. Okay? So I just want to show with all of these formulas, even though they look different, they all have this same property. Basically, they all have that the formulas involve third powers of length inputs. So here it's S times S times S. Here it's L times W times H. Here it's R times R times R. And here it's R times R times H. But in all cases, you're taking three length inputs and multiplying them together. And then maybe with some extra constants. I'm not giving you an interpretation for the constants. But at the very least, a volume formula should involve three length inputs being multiplied together. An area formula should always involve two length inputs being multiplied together. And a perimeter formula should only involve one length input. And it can be multiplied by things like pi or sine of theta, things that are not lengths, but it should not be multiplied by anything else that is measuring length. Okay. Um, Questions on this?
Dr. Obus, it's
Yes, Jasper.
Jasper.
Yes.
Is it in all cases that we replace these variables with either CR or CH?
Mm-hmm. And well, in all cases, so in the cube, you would replace S with CS. In the rectangular prism, you would replace L with CL, W with CW, and H with CH. And in the sphere, you would replace R with CR. The point is, any input that corresponds to a length, you're replacing with C times that same input.
Okay, all right.
Right. So that's what I say, multiplying length inputs by C. So in these formulas, the length inputs are S, L, W, H, and R. They all represent lengths.
Okay.
Yeah. Okay. Other questions?
Yeah.
Yes, Hassan?
One question.
Hassan, yeah, can you repeat? I'm not getting you so clearly.
Yeah.
Yeah. Yeah, Hassan? Do you have a question? I mean, can I say something about how these formulas are derived? Not
Have you
so much
responded to my
now.
question in constructing a geometry? No, it's back.
Sorry, you're coming in and out. I can't get the question.
Yes, man. Are
Mhm.
you getting me now?
No, yeah.
Yeah, I'm concerned about how do you calculate the amount of material needed in constructing a geometrical figure of a
Oh, okay.
specific volume.
Mhm. So you mean you have a hollow container and you want to
Yeah, yeah.
understand how to make a okay. Yeah. So if you're trying to say you want a cylindrical container with a certain volume and you want to know what's the smallest amount of material to calculate it, maybe I can talk about that some other time. That's really a calculus problem, right? So, um, I mean, you have to solve some sort of optimization problem there. So we did that a little bit last year. I can maybe say some more about it later, but not today, because that's really a calculus problem that you need to solve. Okay. Um, okay. So here's an exercise. All right. So I'm telling you that the volume of a dodecahedron with side length 3 is about 206.82. So what is the volume of a dodecahedron with side length 5? Right? And if you haven't seen a dodecahedron before, I can't draw it that well, but let me just show you what it looks like. A dodecahedron is so a dodecahedron looks like this, right? It's a shape with it's a shape that has 12 pentagons for faces. Okay, this is called the regular dodecahedron. I want to see if there's some better, maybe I can find some um, better images of this. Yeah, so I mean, so these are all pictures of a dodecahedron. So this one right here is is a dodecahedron, and there's all these pictures of dodecahedron. It's this solid that looks kind of like a ball, but it has 12 pentagonal faces. So the point is, you probably don't know the volume formula for a dodecahedron. I don't know the volume formula for a dodecahedron. There is one, but it's a complicated formula, and I don't know it. Okay? So, and you could probably look it up if you needed to, but the point of this question is that you don't need to know the formula to answer this question. Okay, so I'm telling you that the volume of a dodecahedron with side length 3 is about 206.82. Okay, so every side of a dodecahedron has the same length. There's these 30 edges that correspond to the sides of the pentagons. So the question is, what is the volume of a dodecahedron with side length 5? Okay? And we just have to keep in mind the principle, right? This thing is a volume, right? So when length inputs get multiplied by C, volumes get multiplied by C cubed. This is what we've just seen, right? Areas get multiplied by C squared, volumes get multiplied by C cubed. So what are we doing here? We start with side length 3, and we're now asking for side length 5. So what's the length getting multiplied? It's getting multiplied by 5 over 3, right? That's how you get from 3 to 5. So in this case, the side length gets multiplied by 5 divided by 3, right? Because you go from side length 3 to side length 5, you have to multiply by 5 over 3. So the volume gets multiplied by, so the volume is going to get multiplied by 5 over 3 cubed, right? And so that means the total volume, well, it's going to be equal to the original volume. That's 206.82. This is what I'm going to call the original volume. Times 5 over 3 cubed. So this I need a calculator to do, or James has probably already done it, so I'm going to trust James's answer. It certainly seems plausible that the answer for this is about 957.44. Okay, I'm sure the answer is right. Okay, and so the point is you don't need to know the formula for the volume of a dodecahedron to answer this, right? You just need to know this principle, that when lengths get multiplied by C, volumes get multiplied by C cubed. And this holds for every conceivable volume formula of anything, okay? And same thing for any possible area or surface area formula for anything. If the lengths get multiplied by C, the areas get multiplied by C squared. It doesn't matter what formula you have. It has to be the case. Questions on this example?
Yes, Dr. Obus.
Yes, Jasper.
Yes, I'm a bit confused as to how you derive at the 5 over 3. Because you said when length get multiplied by C, volumes get multiplied by C cubed. It's understood. So how did he get at 5 over 3? Is it?
Sure. Sure.
Yeah.
I mean, it's just that we're going from side length 3 to side length 5. So it's just saying, basically we're solving the equation 3C equals 5. What do we have to multiply 3 by in order to get 5? And this tells us that C is equal to 5 over 3. Right, because we're starting with side length 3, we're given side length 3, and we want to know what happens with side length 5. So how do we scale from 3 to 5? We have to multiply 3 by something to get 5, and that something is 5/3.
Okay. All right. Okay. All right. See you now. Okay.
Good. Right. Other questions?
I'm sure if you had started like this, that would have got the clear picture of how you got the 5 over 3.
Okay, sorry. Yeah, so I should have started with that at the beginning. Yeah. Okay. Okay, so we're just about done for today, but I wanted to say something, why does this work? Well, let's consider the area of a regular n-gon, where the side lengths s are measured in feet, and then the area is measured in square feet, right? I'm not going to give you the formula for the area of a regular, 12 gon or 20 gon or something. You can look up the formula if you want to, but again, for what we're doing today, you don't need to know the actual formula. Well, what happens to the side lengths if instead of measuring them in feet, we measure them in inches? Well, if we measure them in inches, well, we know there's 12 inches is the same thing as 1 foot, right? So if we change our measurements to inches instead of feet, we have that the length gets multiplied by 12. And well, what happens to the area if we measure it in square inches instead of square feet? Well, in this case, we have that 144 square inches is equal to 1 square foot. Sorry that the writing is a little, let me write this a little bigger. So 144 square inches is equal to 1 square foot. Okay, and that 144 is 12 times 12, right? So what happens is if we have a measurement in square feet, and instead we measure it in square inches, then we get that the area, if we measure it in square inches instead, is multiplied by 12 squared, or 144. And now we say, well, whatever my formula is for area, I mean, formulas don't depend on units, right? The area of a square is s squared, and it doesn't matter whether s is measured in feet or inches or centimeters or meters or light years or any other unit of length that you can have. The formula has to be true no matter what, right? The formula area is equal to s squared, right? That's got to be the formula no matter what. But we just saw here that if you change from feet to inches and you change from square feet to square inches, like the formula better still holds, right? But changing from feet to inches multiplies all of your lengths by 12. And changing from square feet to square inches multiplies your area by 12 squared. No matter what it is, it doesn't need to be a square. If it's an n-gon or a cloud or anything weird, no matter what you do, when you multiply when you change your measurements from square feet to square inches, you multiply your area by 12 squared. Okay, so we're just about done. So what do we conclude from this? Right, the conclusion is so the conclusion is that multiplying length by 12 multiplies area by 12 squared, or 144. But of course, there's nothing special about 12. I mean, 12 just happens to be the number of inches in 1 foot. If I did meters and centimeters, I'd get the same result with 100 instead of 12. If I did feet and half feet, I'd get the same result with 2 instead of 12. So the point is, 12 is arbitrary. Nothing special other than that we happen to have a system that divides a foot into 12 inches, but somebody else could have a system that divides a foot into 9 inches, and why would the geometry in that system be any different? 12 is arbitrary. There's nothing special. So the fact that multiplying a length by 12 is multiplying an area by 12 squared really means, so in general, so multiplying any length by any c is going to multiply area of any shape by c squared. Okay, because you can think of it as just kind of changing the units. If you multiply the length by c, you're just replacing your unit with a unit that's c times is small, like you're replacing feet by inches. And when you do that and you measure your areas, you always have to, just for unit conversions, you always have to just multiply by c squared. Okay, so this is why this principle works. Okay, if you're measuring an area, if you change your units of the sides, you have to change the units of the area by the square of that. And this is showing you that if you multiply your length by 12, you're going to multiply the area by 12 squared. And more generally, if you multiply length by c, you're going to multiply the area by c squared. So this is why this principle has to work. Okay, you don't need any kind of complicated mathematics to make it work, and you don't need to know the complicated formulas. Just for reasons of being able to make unit conversions and still have geometry work, it has to be the case that if you multiply your lengths by some c, then areas are going to have to get multiplied by c squared. Okay, because formulas should work in feet and also in inches. Formulas should work in meters and also in centimeters. And if you want your formulas to work in all of these units, then anytime you make a unit conversion that's scaling by something, then the area has to scale by the square of that. Okay? So, homework exercises. The area of the figure drawn here is 200 square units. I'm just going to draw a figure here. It's going to look like a cloud. That's my figure. So what is the area if I draw the same figure 5 times as big? That means I stretch it by a factor of 5 in all directions. I'm not giving you a formula for how to find this area, but it's just like the dodecahedron problem. You can do this. And the second thing is, can you derive the surface area formula for a square pyramid with height h and base side length s? So this one's a bit of a challenge. So a square pyramid, let me draw the picture for you. So a square pyramid looks like this. You have a square at the bottom, and then you have a pyramid on top. So your square at the bottom has side length s, and then the height is the height from the top of the pyramid down to the center of the square. Okay, so this is height h. Okay, and so the question is, can you derive the surface area formula for this? And once you derive this, can you verify that when you multiply all of the inputs by c, that the surface area gets multiplied by c squared? Okay? So whatever formula you get, it's going to be some formula involving s and h. Um, um, mm, I need, actually, wait a minute. No, that's fine. Yeah, so I'll say this problem is a bit of a challenge. Okay, that this problem is a bit of a challenge. Okay. So if you once you have this formula though, can you verify that when you multiply all of the inputs by c, that the surface area gets multiplied by c squared? Okay. So it's not it takes a little bit of work to do this. Okay, well, I'll send this out, and then next week we'll keep doing geometry. We'll review some of this mensuration stuff, and then we'll talk about some other aspect of geometry. And so, as always, if you haven't put your name down in the chat, in the Zoom chat yet, please write it down so we have your record for attendance. And I will send out the notes and the recording later on this evening. And thank you for coming as always. Thanks for your attention, and I will see you next week. Any questions? Okay, I'll stop the recording.